Welcome back to the Organic Chemistry playlist. In this episode, we are looking at the selectivity of halogenation. What does that mean? Well, if I were to do a monohalogenation, what distribution of products would I expect? Because of course it's going to go on the more substituted carbon, but to what degree? What percent yield are we going to get of that? We'll get to a problem later which shows this quite well. But for now, I just want to go over the theory behind selectivity and kind of explain. I know there's a lot on the board, but it's quite a complex little topic, and once we get to the problems, it will be good to know the theory behind it. So I just want to point out that for the selectivity of halogenation states that, at least for bromine, we'll start with bromine, then we'll get to chlorine. For bromine, if we were to do a monohalogenation of an alkyl group, if we were to compare the rate of which we get a tertiary to a primary, just respectively, they're one for one, they both will get one or the other, we're going to notice that it's going to pick a tertiary alkyl group 1,600 times more than it would a primary. And that's just a relative rate, right? And for secondary, it's about 82 when compared to a primary. These are all with respect to, okay, we form one primary, how many tertiary will we form? Chlorine's a little less selective, you could say, because bromine, it's obviously going to want to select that tertiary, but chlorine here, it's only 1 to 6, and for a secondary, it's only 1 to about 4.5. So you can see the selectivity is a lot different. So how can we explain this, right? Well, it comes down to a lot of thermochemistry and, of course, just looking at the kinetics of this. So I have some reaction diagrams here, and I want you to notice our legend here. If we have a circle that's representing, like the circle part that's representing a tertiary group being formed, a secondary, and a primary is just the solid line. So let's take a look at these reaction diagrams. But before we do that, we need to know that this is in terms of hydrogen abstraction. It's not the full radical process. Remember that propagation step where we take that radical halogen and we rip off a hydrogen and make a radical thing here. So we'll actually draw it out here. We have a bromination with a radical bromine. And just remember, we get hydrobromic acid, and we also get a radical species there. So that's actually what these diagrams are based off of. What's the energy and the kinetics of the step? It's important to realize that for bromine, this is an endothermic process. 42 kilojoules per mole is required for this reaction to occur. But for chlorine, we're actually releasing energy, 21 kilojoules per mole. So that's important when we look at the hydrogen abstraction energy diagrams. So notice this is for chlorine here. This one's for chlorine. Notice how for both of them, the fastest route, the one that goes through the lowest activation energy, is going to be your tertiary. So see here, little hump and then we're good. Little hump and then we're good. Right? So tertiary for both are the most favored. But notice something different. Look at the difference of energies between these. Chlorine, for example, from a tertiary to a secondary to a primary, the difference in activation energy, I'll just say EA for these ones compared to this one is kind of light. It's not very big. But for this, notice how the energy differences in activation energy is so much more. That clues us into saying, okay, well, for this, given the molecules and their energies, some of them are more favorable to just, go up to a primary or secondary or tertiary. They have the energy to do so. And, it's not, molecules don't have brains and say, oh, I'm just going to go tertiary every time because I can. Well, I can also go secondary and primary, and it will do that if it can, just by chance. Depends how fast the molecule's going and how much energy it has to do that reaction. Bromines, it's a little different. Not all these molecules are going to be able to reach these energy states when it's like drastically more. Notice how the primary is like significantly high. Now it's kind of exaggerated here, but notice how this peak is extremely far away from our tertiary peak here. There's a huge change in activation energy between these two. So another thing I want to point out is, why is there such a big energy difference? Well, hopefully from general chemistry you remember the Hammond's postulate. And that's just saying, okay, what's the transition state look like when we reach it? And it says if it's closer to if the energy is closer to your products, it resembles more of your product. And if it's closer, like in this case to chlorine, to the reactant, then it's most likely going to look like your reactant at the transition state. And we can see this here. Look at hydrogen. It's just whoop, and we're there. And we notice that because this is endothermic, we're releasing energy, so it's more resembling of the reactants. And that's what I have shown here. This bond is just starting to break. That hydrogen-carbon bond is just starting to break. Chlorine is just coming in. There is very, 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 very little radical character here. Very, very minute radical character. It's so small. Now, let's take, for example, bromine. Notice how we are really close in energy to our product. Well, that probably tells you that it's resembling a lot like the product does. That means that this carbon-hydrogen bond is almost broken, and the hydrogen-bromine bond is just forming. This means there is significantly more radical character here. There is basically a radical there. And that radical character is realized, and we know that the differences in energy between that is only realized when there's a radical there. Here, not so much. Here, definitely. And you can see that. That's why the selectivity is 1600 to 1 and chlorine is 6 to 1. All right, that was a lot. Hopefully that makes sense. I want to now get into a problem where we apply this stuff, because you can know it, but how do you apply it? So let's get into that now. Okay, so I have this problem here where we're going to have a simple monohalogenation. Now, you might have been told draw the major product, and if that's the case, you'd put a bromine here. Right? Remember, this is symmetrical, so if I put it here or here, it wouldn't matter. But just realize that if you were asked by your professor draw the major product of this reaction, you'd put it on the tertiary. But I'm not going to ask you that. I'm going to ask you, what are all the products possible in this reaction for a monohalogenation, not a dihalogenation or polyhalogenation, just a monohalogenation? What are all the products, and what are their relative rates of, or their yields when they are formed? So let's go through it. Notice that there's a plane of symmetry. That is intentional because I do not want to torture you. So we will treat one half of the molecule just like the other, because if we add one bromine to one side, it will be the same on the other. Okay, so let's draw all the products we could physically make for a monohalogenation. Well, I know that we could make a tertiary product where I put a bromine in the tertiary position. I know I could also make a primary, so I'll make a primary one. And I want you just to realize there's only one primary product in this reaction, because this bond is free to rotate, and if I just took this bromine and I took this bond and I rotated it, it would be the exact same as putting it on this carbon here. And remember, that plane of symmetry means I could put it there or there. So just thought I wanted to point that out to clear up any confusion. All right, and then for our last one, we could also get a secondary, and I hopefully this one doesn't come as too much of a shocker, but right there we have a secondary alkyl halide. So we have our alkyl halides. What are their rates of yield when, if we were to put this, this would be dimethylpentane. If we put dimethylpentane with our bromine gas and we gave it photochemical conditions, what would be the yields of all these products that we would expect theoretically? Well, the math can be kind of tricky, so we're going to go through it now. So the first step of this is count hydrogens per position. Kind of sounds complicated. Number of H's, we'll simplify it. What do I mean by that? So how many hydrogens could we abstract and then attach our bromine to to get the product? Well, for the tertiary, for example, we know that there's a hydrogen here and a hydrogen here. There are 2 hydrogens that could make this product. So we're going to write 2H. Hopefully you can kind of see the pattern now. It's a little hard to describe. Now let's go for our primary. For our primary, what would that be? Well, we have 3 hydrogens here, 3 hydrogens here, 3 there and 3 there. That gives us a total of 12 hydrogens. All right, and then we look at our secondary, and we know that there are 2 hydrogens, 1 there, 1 there. So that gives us 2 hydrogens. Step 2 of these problems is to multiply by selectivity factor. So our selectivity factor says, okay, for every primary, we'll make 82 secondaries and 1,600 tertiaries. So we'll start with tertiary. We multiply it by 1,600. For primary, again, just 1. And then for our secondary, we have a selectivity factor of 82. And let me grab my calculator quick so we can get the sum of these. So 2 times 1,600, I should know that. I don't know why I just typed that in my calculator. God forgive me. 3,200. All right, and this is 12. And not too sure what that is. 164. All right, so these are the relative. If for every 12 of these we make 3,200 of those and 164 of those. Quite simple. Now let's get the sum of all these values. So I'll just draw a sum sign. Get the sum. 3,200 plus 12 plus 164 is going to give us a sum that is 3. That was not a 3. 3376. All right. This number is going to be important because now we are going to find, we're going to do this simple formula here, which is, we'll do, I'll call it H times selectivity factor over sum times 100. And what will that give us? That will give us a percentage of each relative to each other. So hopefully that makes a little bit of sense. And I'm just going to draw, to make some room, I'm going to draw our sum over here instead. And we're going to go here. So for the tertiary monohalogenation product, that's, drop my calculator, 3,200 over 3376 times 100. What percentage of our product will be that? 3,200 divided by 3376 times 100. We would get an expected theoretical yield of the tertiary product to be 94.8%. We'll round to 3 sig figs. Looks like, yeah, doesn't really matter. Sig figs are not important here. Okay, so 94.8% of your product will be tertiary. What about our primary? Even though we have 12 hydrogens, we're going to see that, well, it's not going to be that much. So that would be 12 over 3,376 times 100 to give us 0.35%. So very, very minute. Even though those hydrogens are all there, there's 12 of them compared to the 4 other ones on the molecule. You're only going to get like less than 1% of that product. All right, and then for our secondary, I bet you're already beating me to it here. So this would be, oh goodness, yes, 12 and then 164. I had a brain fart, everyone. Don't you love when that happens? God bless. Okay. 164 divided by 3376 times 100. And that's going to give us this product's yield to be 4.86%. So that's the selectivity math section of it. We looked at the theory and why this selectivity occurs. Now we did a practice problem. I hope that these calculations aren't too terrible for you. For me, they kind of make sense, but I know for some people it can be kind of challenging, and that's okay. I hope you guys enjoyed. Thank you guys so much for watching.